Okay, our next speaker is Nathan Lindzey from the University of Colorado at Boulder. The title of his talk is on the algebraic combinatorics of injections.
Thank you very much for the introduction. So this talk is going to be of a much more applied nature. So I suspect that everyone's going to be able to follow this without any problems. But I think that the open questions that arise in this work are going to be interesting to this community. So I really appreciate the opportunity to speak in front of the FPSAC community. Okay, let's get into it. So this is joint work with Peter Dukes and Ferdinand Iringer. Okay, so injections. So SKN is going to be the set of all injective maps. So it's not too difficult to see that these are counted by the following factorial. And when K is equal to N, we get permutations. So the theme of this talk is going to be to generalize what's known for permutations to injections. Okay, so here's a quick example. So E is the injection that sends 1 to 1, 2 to 2, 3 to 3. And sigma is the injection that sends 1 to 2, 2 to 1, and 3 to 5. And so throughout this talk, we're going to represent these injections graphically as K-matchings of a complete bipartite graph. So here we have we see that we get, thinking of this graphically, the union of these two is a 4-cycle and a 2-path. Okay, and so E is going to be a distinguished injection throughout this talk. So we're going to call that the identity injection. And sigma is just going to be an arbitrary injection. Okay, sorry. Okay, so it's not too difficult to see that if we take this graphical union of E and sigma, then we're always going to get a disjoint copies of an even length cycles and even length paths. Okay, and so it's not too difficult to identify these isomorphism types with pairs of partitions, lambda and rho, where the size of lambda plus the size of rho is forced to be equal to K, and the number of non-zero parts in rho has to be less than or equal to N minus K. So let's see an example, or sorry, let's actually define one more thing. So we're going to call C sub lambda rho. So these are going to be all the injections such that when I take this graphical union of E with sigma, I get a graph that's isomorphic to lambda rho. So we're going to call this a cycle path class. And you should think of this as like a generalization of conjugacy classes in the symmetric group. So here's a few examples just to be sure we're on the same page. So E is in its own cyclopath class. And let's take a look at sigma here. So sigma, I have the blue sigma, I have a 4-cycle and a 2-path, and I'm going to divide those lengths by 2. And so what I'm left with is is 2 bar 1 comma 0 2. And these zeros here kind of represent the fact that I have some paths of length 0, namely in this example 4 and 6. So those are paths of length 0. Okay. So this immediately gives a nice way to decompose injections according to their cyclopath classes. And as one would expect, there's a nice generalization of the count for conjugacy classes of the symmetric group. So when K equals N here, we recover that count. And so here we have this N minus K and this factorial and this Ri factorial. And those pop up due to the fact that we have to be counting paths now as well as cycles. Okay, so this begs the question, are there other counts that are reminiscent of what we get for the symmetric group? So how about RSK? So Laura did a wonderful job of explaining RSK to everybody, so I'm just going to jump right into it. So these injections, we can encode them as generalized permutations. So, and that encoding is listed above. Okay, and so by the RSK correspondence, we get P and Q. So P is going to be a standard Young tableau because my bottom row, I have all unique entries. And on my top row, my recording tableau, I'm going to have some repeated entries. So it will be actually a semi-standard Young tableau. But these K plus 1 these cells labeled by k plus 1, they're kind of redundant. So we actually can throw them out. So so this horizontal strip of k plus 1s, we don't really need them for RSK. And so this example will perhaps make this clear. So here's an example for k equals 2 and n equals 4. So here's our nice bijection between two injections and pairs P and Q. And so these X's kind of, these are where we would have the cells of labeled 3, and we've just gotten rid of those. So now we have two standard Young tableau, but of different shapes, where the two shapes differ by a horizontal strip. Okay, so we immediately get a count now for the injections, where we are summing over pairs mu and lambda, such that the skew tableau, lambda mu, is a horizontal strip. So a horizontal strip, I'll go ahead and define that. So that's just it's a skew tableau where there's no two cells on top of one another. Okay, so there's a lot of this, there are a lot of nice things in this count here. So when you see horizontal strip, you probably think of Peary's rule. And when you see these F mu, F lambdas, so F mu is the number of standard Young tableau of shape mu, and respectively for lambda, you probably think of standard Young tableau, as you should. And so this begs the question, is there a representation theoretic proof of this? And it turns out that there is, and we'll go through that. And so so the F mu, F lambda, this is begging to be counted by spec modules. Okay, so the question is, do we have, is there a permutation representation, VKN? So where I have SK cross SN acting on injections, such that I get the following decomposition into SK cross SN irreducibles. Okay, where mu and lambda are required to differ by a horizontal strip. Okay, so for this, one needs a two-sided action, and this two-sided action is defined as follows. So we're acting on, so SK is acting on like the left side of the graph here, if you want, and SN is acting on the right side of the graph. And it's not too difficult to see that our distinguished injection E. So if I wanted to look at the stabilizer of that, then that's simply the diagonal subgroup cross of SK cross SK cross SN minus K. And so this is easy to see. If I move something on the right hand side, if I move 1 to 2 on the right hand side, then I also have to do that on the left hand side. I have to move 1 to 2 on the left hand side. And the SN minus K factor appears because we can scramble the remaining vertices however we wish. Okay, so some standard representation theory at this point. So we have this permutation representation, and so by transitivity of induction and Peary's rule, we can we can prove what we sought out to prove. So we have the following decomposition into irreducible representations of SK cross SN. So what's excellent about this is that this is a multiplicity-free permutation representation. And so in harmonic analysis, multiplicity-free means that you have you have a commutative algebra somewhere often. And so in combinatorics, in algebraic combinatorics, which is what I study, this means that we have a symmetric association scheme, in fact. And so we'll define what that is here on the next slide. Okay. So this association scheme, if you haven't seen them before, these are very nice commutative algebras that are often combinatorially inspired, and they pop up in a lot of applied scenarios. Our injection scheme is going to be just a collection of binary matrices that are indexed by injections. And we're going to have that 2 injections, sigma and sigma prime. So there's going to be a 1 for that corresponding entry. If when I take their graphical union, I get the cycle type lambda rho. And so remember that lambda is is keeping track of cycles in this isomorphism type, and rho is keeping track of paths. Okay, and it's going to be a 0 otherwise. And so we do this for each cycle path type. Okay, and so as I said before, this is a basis for a commutative algebra. And so in statistics coding theory, this is often called the Bose-Mesner algebra. If you prefer, this is a Heck algebra, where my double cosets are given by my big group SK cross Sn and my small group, which would be the stabilizer of E. Okay. And what gives association schemes their charm is that there's this canonical dual basis of primitive idempotents, which are, and these primitive idempotents are just the orthogonal projectors onto the SK cross Sn irreducibles that pop up in VKN. So these are the, so remember these irreducibles are the ones where I have lambda on N cells, mu on K cells, such that their skew tableau gives me a horizontal strip. Okay, so for permutations, we have this this wonderful correspondence between cycle types, partitions, and irreducibles of Sn. So a natural thing to wonder is, does this generalize to injections? So is there a canonical way of associating an irreducible of VKN with cycle types of SKN? And I will do a bijection by picture here. So the answer is yes. So let's just look at this first one on the left here. So k equals 3, n equals 7. So lambda in this picture is 4, 2, 1, and mu is 2, 1. So their skew tableau is a horizontal strip. And I'm going to look at the columns here, and if I see an x, so if my horizontal strip touches that column, then that's going to correspond to a path. So and if there is no horizontal cell of a horizontal strip that touches the column, then that's going to correspond to a cycle. So in this first example, I have all paths. I have a path of length 2, a path of length 1, and 2 isolated paths. In the next one, I have one single cycle. I have a path of length 2, and I have 3 isolated nodes, and so forth. So we get this nice bijection between irreducibles and cycle path types of SKN. Okay, so the P matrix of a association scheme. So some of you might know this as so the P matrix is just it's a generalization of the character table of a group. And so in our case, so the group character table of Sn would be indexed by conjugacy classes, and those are indeed cycle types of Sn. So in our case, we're going to be indexing this matrix by cycle path types. And so dkn is going to be the number of cycle path types. And so this P matrix is simply, it's just a table where we're collecting eigenvalue information about our basis elements. So these A matrices. And so each of these primitive idempotents, it turns out it's not too hard to show that these are actually the projectors onto the eigenspaces of these graphs. So the eigenspaces of these graphs are irreducible representations of SKN. And so this P matrix is just a way of collecting all this information into a nice table, and you recover the group character table up to normalization this way. So the main question behind this work is whether or not there are good formulas for computing entries of P. And so for instance, for the symmetric group, I would say there's a good formula known as the Murnaghan-Nakayama rule for computing these entries, but it's unknown whether or not there are similar nice combinatorial rules for computing the character table of the injection association scheme. And so it turns out this is an old question that was asked by Percy Diaconis and Andy Greenhall back in 1989. So they stumbled across this association scheme in some of their work on random walks, Markov chains, mixing times. And it's recent. This association scheme has recently reared its head as in quantum query complexity, which is a branch of theoretical computer science and quantum computing. So there's several papers where this injection association scheme has been encountered, and progress was thwarted by the fact that we didn't really have any good formulas for these entries of P. And it also comes up in coding theory. So in 2012, Peter Dukes, one of our co-authors, started looking at codes that over injections, and we'll have time to talk about that later. Okay, so I want to say that there's kind of an off-the-shelf, not so good formula for the P matrix, and it's as follows. So to keep this formula tidy, I'm going to just let I and J be cycle types. So you should think of I as corresponding to some pair of partitions, and J as corresponding to some pair of partitions. Right, and so G is going to be SK cross SN, and K is going to be the stabilizer of this identity injection. Okay, so here's a formula for the eigenvalues. So it's this, so you could call this the projection of these characters chi onto the space of K invariant functions. Another way to see this is that this is essentially the ith spherical function of the Gelfand pair G comma K. But the problem with this formula is that it is difficult in both theory and practice. So if I wanted to just compute the P matrix for modest values of N and K, and I had this formula, I would get stuck pretty fast. And also, it's near impossible to kind of get some nice formulas by just staring at this projection formula. So the main contribution of this work was to get a better formula for the P matrix. I wouldn't call it a good formula, but it's better. And with this better formula, we've been able to progress the state of the art of a few things and where this association scheme pops up. So we'll describe this better formula. So S is going to be a mu tabloid, and T is going to be a lambda tabloid, such where they're of respective shapes mu and lambda. Okay, and so we have this combinatorial definition. So I have S. I'm going to say that the tabloids S and T cover an injection sigma if, when I look at the index of the row in S in which I resides, that is the same as the index of the row in T in which lambda I resides. So this is best explained with a picture, and so I will, or illustrated with the picture. So I'll give a quick example here. So K is going to be equal to 5, N is going to be equal to 8, and so so the bold letters are going to be S, and the non-bold letters will be T. And what I want to do is, so to make this picture easy, I'm going to kind of merge these two tabloids together to get this meta tabloid. So we see that down here at the left. So we see that the identity injection and this injection sigma, or this blue injection, they're both covered by S and T because I don't have any, so thinking of them as matchings, K matchings, I don't have any edges that go from one row to another row. Like all the edges are aligned in the same row. Whereas this green injection over here, this green injection is not covered by S and T. And it turns out, even if you start permuting entries in the columns of T, you still can't find a way to cover this green matching. And so we'll see why that's important in the next slide. But so that's the definition of what it means for two tabloids to cover an injection. Okay, so here's our better formula for entries of the P matrix. So again, I'm going to make things tidy and let J be a cycle type, and I'm going to let I be a cycle type. So here are these primes. They just denote, they don't denote transposition. They're just different cycle types. And so here I have this mu lambda. So remember that that there's this correspondence between irreducibles and mu lambda that differ by a horizontal strip. And so this arrow here is just denoting that bijection. And so what I have here is a combinatorial formula that's a signed sum of combinatorial statistics for tabloids S and T, where S and T are standard Young tableau of shape mu and lambda respectively. So I'll say a few things about this proof. I think that the details are not so important, but the way that we came across this was first we gave a basis for the space of complex valued functions over injections in terms of polytabloids. And so some of this will look familiar, right? So I'm summing over permutations in the column stabilizer, and I'm looking at the sign here. So that reeks of polytabloids, right? And so so we found an appropriate intertwining map that intertwine the permutation representations and these irreducible and these pairs of SK-SN irreducibles. And then from there, you have to do some finessing to get a formula as nice as the right-hand side. But I think it's all it's not an unreasonable amount of work to arrive at this formula. Okay, so maybe a quick example. So back to this green injection that we talked about. So for instance, this green injection here would contribute 0 to this sum here, because there's no way that I can permute the columns of T so that I get this green injection to be covered. So what you can do with this formula, we don't talk about it very much in the paper, but you can actually start to say concrete things about the eigenvalues of certain matrices in these association schemes. So you can get, and for special values of J and I, you can actually get closed formulas, but certainly not for all I and J. So this is, like I said, this is just the first step towards getting a good formula for the P matrix, where we have a, yeah. So I guess I'll leave it at that. Okay, so right, so I'll briefly talk about the applications of our work. So we applied it to injection codes. So these were defined by Peter Dukes in 2012. So an injection code of length K and minimum distance D is just it's a set gamma, such that if I look at any two elements, so any two injections, I have Hamming distance greater than or equal to D. Okay, so what do we mean by Hamming distance? Well, it's kind of what you would expect. So first I should say, that in the case where K equals N, then we have permutation codes. And these are well-studied objects in coding theory. And they have some interesting applications to power line design and so forth. So so here's an example. So by Hamming distance, we just mean, we're thinking of these injections as being coordinates with numbers. And so these two injections have Hamming distance too, because they agree everywhere but the first and last coordinates. Okay, and so MNKD is just going to be the maximum size of gamma. And so a coding theorist is interested in upper bounds and lower bounds for these codes. So like, how large can I make gamma? So we kind of like knowing these bounds. And so in the case where K is equal to N, so if I looked at M, N, 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 then that equals N. And this is just, it's not difficult to see that this is just due to the fact that Latin squares exist for all orders. And even if I change D to be 1 less, so N minus 1, then we start bumping against like some really hard problems in finite geometry. So like knowing whether or not a projective plane of order N exists. So permutation codes are a very difficult object to study. And so it was suggested by Peter Dukes that we should look at a relaxation of permutation codes, injection codes, as an intermediate level of difficulty. But the problem was, like, even though you can define such an object, you still need to have data and know like the behavior for small n and k in order to make any sort of conjectures about these codes. And there really wasn't any formula for that prior to this work. And so the better formula advanced the state of the art for these injection codes. And this was recently accepted into IEEE Transactions on Information Theory. Okay, so I have 2 minutes for open questions. So some of you are probably wondering, where's the FPS? There's a lot of AC going on, but I don't see any FPS. And that's precisely my open question. So, so I think many of us are probably aware of the characteristic map between this algebra C, which is generated by all irreducible characters symmetric groups, and the ring of symmetric functions. And so my question is, can we study the P matrix, the characters of injection schemes? Can we study them from a ring theoretic point of view? So is there an analogous characteristic map in an analogous ring, lambda prime, for SKN? And so can do some sort of character theory of SKN in this ring. And there's some partial results in this area. So Eugene Strahov did this in 2008 for k equals n-1. And the k equals n-1 case is a lot nicer than the other cases. But at least there's some work in this direction. And then in particular, if such a theory does exist, then you can start looking at transition matrices like you would in the theory of symmetric functions. And one thing that I'm particularly curious about is an LU decomposition of the P matrix of SKN. So I want to write the P matrix as the product of two transition matrices, where one's lower triangular and the other is upper triangular. Okay, and I'll conclude with some algebraic combinatorics questions. So can we classify Gelfand pairs of the form SK cross Sn, comma H? So Saxel did this for the case where K is trivial, where SK is trivial. And perhaps there are other unbalanced Gelfand pairs, kind of like the one we saw here for finite groups of Lie type. So I haven't seriously investigated those questions yet. And that is all for today. Thank you for listening.
Thank you, Nathan, for your very interesting talk. You can stop sharing your screen now, so you can see the reactions from people. And let everyone thank the speaker for Twitter reaction. Now we have about 4 minutes for questions, and I will turn things over to our chat monitor, Amy Pan.
So, Pyong Huang says, very naive question. Is there a connection with Kronecker coefficients or Littlewood-Richardson coefficients?
I would say the only connection is that Peary's rule is kind of a special case of the Littlewood-Richardson rule. I don't know if that answers your question, but I guess the thing is that I'm not really looking at I'm not looking at multiplicities of so I guess this would be I guess I should probably just say I don't know the answer to that question, but I'm not aware of it.
Okay, Alejandro says, is there a notion of a dual code?
The notion of a dual code. I suppose so. So I guess you could say, so these codes correspond to cliques in particular. So these A matrices, you can view these things as graphs, and you can start looking at graphs that live in this Bose-Mesner algebra, and these codes correspond to the size of the largest, or they're just cliques in these graphs. And so the size of a largest clique would be the size of a maximum code for particular parameters. So I guess a dual code perhaps would be independent sets, or you can look at the complement of that graph. And in these independent sets, then these start brushing up against Erdős-Corrado type questions. So if you know what that is, great. If not, it's not too important. But I guess that would be what I would define a dual code. I'm not really a coding theorist, but perhaps I can run that by my co-authors and see if that makes sense.
Okay, and Alejandro also asks, do the bound on the M's give bounds on the sums of characters?
there is some relation here between sums of characters and bounds on M. In particular, these bounds on M come from a linear program that's called Delsart's linear program, and essentially we're looking at the Q matrix of the association scheme here, which is essentially the inverse of P. So there is some connection here between sums of characters and bounds on M.
Okay. And Jiahuan Wang says, are there nice behaviors of the P matrix if you pick interesting K and N?
So I suspect if you fix K, for example, then you should be able to just write down a polynomial that gives you the entries of P. What to me, the interesting case is when K is not constant and it varies with as some function of N, in which case I can't really, I really don't know what's going on. But to give a more concrete answer to your question, so if for constant K, I would suspect yes, you could just write it down. And for K equal to N, we just recover the symmetric group up to normalization. And for K equals N-1, you get Strahov's work, which is a very beautiful and easy to read paper. If this interests you, then that would be one of the first places to start.
Okay. Yuval Thomas asked, what about the Q matrix? What can you said you are interested in? I think this is about the part where you said you're interested in the P matrix.
Mm-hmm.
But what about the Q matrix?
Right. So as far as I know, so you could make the argument that if once you know the P matrix, you know the Q matrix by just by inversion and multiplication by a scalar factor. But it could very well be that there are there are certain entries of the Q matrix that are easy to read off. I haven't really considered that. Most of the things that, most of the applications that I've had my eye on, you kind of want to know the eigenvalues of certain graphs that live in this association scheme. But yeah, it could very well be that there are nice formulas for special, for restricted values in cycle types for the Q matrix.
Okay. Yep, those are all the questions that were asked.
Great.
Okay, let us thank again our speaker. And thanks for all the speakers we had today. And now we are going to the coffee break.